Hello everyone. Today we are going to discuss on kinematic indeterminacy and shortcut procedure to calculate this kinematic indeterminacy. This is the second part of the element of structural analysis and its introductory discussion. So we have to recap about the previous lecture. Previous lecture video link has been mentioned in my description box given below this lecture. So what we have discussed in the last day's lecture, that we have discussed the definition of the structure first, and then discussion on restraint and how different kind of restraints forms a support. Concept of degree of restraint and degree of freedom, which actually gives us the method or the tool to calculate the statical indeterminacy and as well as the kinematic indeterminacy. Statical indeterminacy has been discussed in the previous lecture. Now today we will discuss on the kinematic indeterminacy. We have also discussed about the example how to calculate statical indeterminacy for beam, truss and portal frame of different support condition and consisting of hybrid joint. In this lecture also we will follow the same line of discussion, that is we will first discuss on beam, then we'll go to truss and then we will discuss on the portal frame. Discussion and calculation of the stability in terms of indeterminacy have been also discussed in the last day's lecture. Today we will also try to discuss on the instability criteria on the light of kinematic indeterminacy. Here is the picture of our first day's lecture or the part 1 lecture of the structural analysis series, and the link is shared in the comment box. Degree of kinematic indeterminacy, DKI. What is that? The numbers of unknown independent movement in the structure with which the kinematic configuration of the overall structure can be defined. It is known as kinematic indeterminacy. So the how many numbers of independent movement, and also a key point must be added in this is possible independent movement. It should be possible, means we are not considering any type of external load here, but we are considering whatever may be the load, what are the possible independent movement. Why independent movement? Because if one movement is equal to another movement or displacement, we should not consider it as another degree of freedom separately. So if it is separate than each other, then only we will consider that as a kinematic indeterminacy calculation. In a plane structure, there are three possible directions of movement in a joint. In this present lecture, we are going to consider the plane structure itself. In the subsequent discussion, we will take care about the 3D or space structure. The possible displacements are in x direction, we may say horizontal displacement or translational movement, y direction or vertical direction, or maybe called as a transverse movement, and a rotational movement also may possible in the plane structure. The types of the support and the joint describes the possible degrees of freedom, because there may be some restraint along this considered three direction, so accordingly the degrees of freedom will be decreased. So here is a table where we are considering different support condition. First of all, we have considered hinge joint, where we will see there is a rotational degree of freedom. So a hinge joint have two restraints that we have already discussed, but here we will only consider about the degree of freedom. There is a rotational degree of freedom. In the roller joint, you will see we have two degrees of freedom. One is rotation, another is translational movement. That is, it may move along the horizontal direction. So this is adding up one extra degree of freedom in compared to the hinge. So nextly we are considering the fixed joint, where we will see there are no degrees of freedom in the joint, because all the three possible direction of movement are restrained, or we may also term it as a clamped joint. In the fourth one, we will see that there is a guided roller where only horizontal movement or translational movement is possible, and we may say that it is having degree of freedom. We we used to also consider different hybrid joints in the structural member, where we will see different kind of forces are released for specific purpose to be served by a structure. So first type is internal hinge. We also used to call it as a moment release. It has only 1 degree of freedom, and rotational release is there. Shear release is one where transverse movement is allowed, again 1 degree of freedom, and axial force release is also there for a specific type of joint, where we will see the translational movement in x direction is allowed. So it have 1 degree of freedom. Let us come to a mathematical expression, where we will see the kinematic indeterminacy Ki is equals to possible independent joint displacements, which is caused due to the related displacement from the support and the displacement which is allowed in the hybrid joints. Let us take some example so that we can calculate the kinematic indeterminacy very easily. Let us consider a cantilever beam, which is the most simplest structure that we can consider. This is the cantilever beam, and we have one vertical, one horizontal, and a rotational degree of freedom, because it is a free joint. At the free end there is no restraint. So this is the deflected pattern, how it deflects under the load, or we may say the elastic curve of the deflection. So possible independent joint displacements are 3, and we can see here the axial movement, which is very small in compared to other two, that is transverse and rotational displacements in case of beam. So we have ignored the axial deformation, and by ignoring the axial deformation, the kinematic indeterminacy boils down to 2. So we may say kinematic indeterminacy of this beam is 2. Let us consider a simply supported beam with a hinge joint at the left end and a roller joint at the right end. So let us consider the possible degrees of freedom. For hinge there is a rotational degrees of freedom. All these has been referred in the previous table. In roller joint there will be a translational movement and a rotational movement. Possible degrees of freedoms are 2. So in total there is possible independent joint displacement. There are 3 possible degrees of independent joint displacements. So again we will ignore the axial deformation. So the translational movement in roller joint will be excluded, and the axial deformation exclusion will boil down the kinematic indeterminacy to 2 of this specific structure, that is simply supported beam. So kinematic indeterminacy is equals to 2. Let us now consider an overhang beam where there is a hinge joint in the left and a roller joint in the right end. By the way, I must refer here all the structure which are being considered in this lecture for calculating the kinematic indeterminacy are being considered in the previous lecture also for calculating statical indeterminacy step by step. So here let us come back. There is a rotational movement in the hinge joint and a rotation at the roller, as well as translational movement. But again we will see there is a overhang portion or cantilever portion. So there will be a theta, again a slope there, and in the free joint there will be a deflection and a rotation in the free joint. But you see the axial deformation of the beam again will be ignored. So the translational movement or the possible degree of freedom in the translational direction in the roller joint can be ignored. So we may say possible joint displacements are 5 here. 3 rotations and 2 displacements or the deformations in the free end, 1 rotation and a deflection. But you see here again, due to continuity of the beam, as it is continuous over the roller support, you may see here this is having the continuity over the roller support. So phi, the rotation in this joint is equal to rotation in this joint. So phi is equals to psi. So we may say that it is actually not two independent displacement, it is only a one independent displacement. So possible independent displacement, possible independent displacement is coming down to 4. Now here we will see the rotation at the free end and the displacement at the free end is not associated with any force. It will not generate any bending moment shear force in the free end. So it may also be ignored. Now the kinematic indeterminacy of this overhang beam is coming down to 2. Let us go to next problem. A fixed ended beam. If we put a load on this beam, it will deflect like this. This is the deflected pattern, or we may say the elastic curve of the beam. The possible independent joint displacements are 0. So the kinematic indeterminacy of this beam is 0. We may say this beam is kinematically determinate. Let us now consider this continuous beam with two supports. At the leftmost support there is a hinge, and the rightmost support there is a roller, and there is an intermediate support at the intermediate portion of the beam. So if this is the deflected pattern, here again you can see there will be a possible displacement phi here and theta here, but these two displacements will have to be equal because there is a continuity between this. So there it is opposite angle, so it should be equal, and all these two will be psi, and it is, though it is unknown, but there will be no two independent, but this will cause a one independent unknown displacement. So there will be 3 independent joint displacement. Again, we will not consider the axial deformation, so the translational movement in the roller joint will not be considered. The possible joint displacement will be 3, and the total kinematic indeterminacy of this beam will be equals to 3. Let us now consider this propped cantilever. This is the deflected pattern, and as we can see in the rightmost support there is a hinge, and that caused a rotation of phi in this joint. So there is one possible joint displacement, and the kinematic indeterminacy will be equals to 1. I must refer here, if this joint instead of being hinged it may be a roller, then also the translational movement or the horizontal movement of the roller joint must be ignored, because the axial deformation of the beam is generally ignored unless otherwise it is mentioned to consider. So here again it should have the kinematic indeterminacy is equal to 1. Let us now consider a propped cantilever which is having a hybrid joint or a internal hinge at the center. So what we will see, there will be 2 independent joint rotation. So there is a 1 displacement due to hybrid joint and 1 rotational displacement due to the hinge joint at the right support. So kinematic indeterminacy of this type of beam will be equals to 2. Let us now consider this beam, that is a simply supported beam having a hybrid joint at the center, which is a internal hinge again, that is moment is being released. So you will see there will be 1 independent joint displacement due to the hybrid joint, and there will be 2 independent joint displacements or the rotational joint displacement at the hinge, one at hinge and another at roller. So that one rotation at hinge and one rotation at roller, and the rotation at this internal hinge will boil down to 3. So we may say that this is having kinematic indeterminacy equals to 3, but you see the configuration of the beam, the kinematic configuration. If there is a load from the top side, it will fail due to rotation, unlimited rotation, and we may say from the kinematic configuration of the structure that the beam is unstable. Again, let us consider this as a beam, a simply supported beam having two rollers in each of the joints, each of the support. Okay, so if we consider the possible independent joint displacement, it will be 3, because there will be two rotations and a translational movement in the beam. So we may say the kinematic indeterminacy, neglecting the axial deformation, we may say that there is two kinematic indeterminacy, but this kinematic configuration shows that there is a chance of rolling out of the beam in horizontal direction. In that case, we may say that kinematic configuration shows us that the beam is again proved to be unstable. So let us come to some conclusion about the beam. Kinematic indeterminacy of a beam is always measured according to the possible independent joint and support displacement. Axial deformation of a beam may be ignored unless mentioned otherwise to considered. Higher the indeterminacy of the structure, higher will be the chance of instability. But the structure turns to mechanism if there is no restraint against any possible displacement. Here in the last two structure we have seen there was no such restraint against the movement of the possible deformation, not even in a single joint among the two, so it has failed due to forming a mechanism. Let us consider the truss. In the previous lecture, we have defined here for recapitulation. Again, we are defining the truss. Truss is a pin-jointed structure subjected to axial force only. There will be no generation of bending or shear. So, axial load, either compressive or tensile, will be generated in the truss. So there are two possible displacement in each joint in the truss. One is vertical, another is horizontal movement. So there will be, and each and every joint of the truss there will be 2 degrees of freedom. So kinematic indeterminacy of the truss will be two numbers of joint, two into numbers of joints minus the number of support restraints. Let us consider an example. Here we can see a truss having 1, 2, 3, 4, 5, 6 numbers of joints. So we may say numbers of joints are 6, numbers of possible displacements are 6 into 2 is equals to 12, and numbers of restraints are 2 in the hinge because it does not allow vertical and horizontal movement, and there will be 1 along the roller. It will not allow the vertical movement. We are not considering the rotation here because all the joint is possible to rotate because all the joints are pin jointed. So what should be the kinematic indeterminacy? It is equals to 2 into 6 minus 3 is equals to 9. So there will be 9 degree of kinematic indeterminacy of this truss. Let us come to another example. This truss, which is having two hinge joints having 4 numbers of joints. So numbers of joints are 4. Numbers of possible independent displacement will be 2 into 4 equals to 8. Number of restraints are 2 in each hinge joint. So there will be 4 numbers of restraint. So the total restraints are equals to 2 into 2 equals to 4. So kinematic indeterminacy of the truss will be 2 into 4 possible displacement minus 2 into 2 is equals to the restraints. So it will boil down to 4. That is, the truss is kinematically indeterminate by degree 4. Let us now consider this truss where we have again 4 joints and there are 2 restraints, vertical restraints. So we may say the total numbers of restraints are 2 and the numbers of possible displacements are 8. So it may be said that the truss is kinematically indeterminate by degree 6, but here again the possible horizontal movement have no restraint. So the kinematic configuration shows us that the truss is unstable as per the kinematic configuration. So let us come to the next part, the conclusion of the truss. Axial deformation of the truss should not be ignored because there is only an axial deformation in the truss, so it should be considered. And the higher the kinematic indeterminacy, again it is the stability problem. Rigid jointed frame. Again we will say here, what is rigid jointed frame? If this is a frame and under the load it deforms like this, but the angle between the deformed configuration and the undeformed configuration, if it requires, it remains equal. If it remains equal, the frame is said to be rigid jointed frame, whereas truss may be termed as pin jointed frame. Here again we have written it, rigid jointed frame are those where angle between the member remains unchanged in deformed state. So let us consider a portal frame. We may also say it as a portal frame, which is simplest portal frame having two fixed joint. This is the deformed pattern. There will be two joint rotation. So there is possible joint rotations which is independent. Now if there is a horizontal load, we may say these are the joint rotation. If there is a horizontal load, there will be this kind of deformation along with the joint rotation. So we may say this as a floor sway. So considering numbers of possible displacement, two rotations and one number of floor sway, the kinematic indeterminacy is coming as 3. One thing we want to note here, if there is a possible axial deformation in the floor, the sway in this joint, that is in the right joint, should not be equal to the left joint because there may be elongation. But here in this present case we have not considered again the axial deformation, so the kinematic indeterminacy is coming as 3 because the sway is only 1, because this sway movement has caused, if this is a delta in this right joint, it is again delta in the left joint itself also. Now let us consider this multi-storied multi-bay portal. There are 2 stories and 2 bays. So numbers of rotations are 6 in the rigid joints, and there will be 2 rotation possible in the supports. One is hinge, another is roller. So there will be a possible translational movement in the roller joint itself also. So we have said there are 8 rotation, 1 translation, and there are 2 unknown sways, possible displacements. Mind it, these are all possible displacements. We have not considered any load here. So the sway at the top level should not be equal to the sway at the first load level. So it should be independent unknown, and the kinematic indeterminacy of this frame is boiling down to 11. Now let us consider this complex frame. Here we have a hybrid, 2 hybrid joints. One is this one, the rotational release and a shear release at this joint, and there is a rotation at the there is a possible displacement in the this guided roller, and there is also a secondary cantilever frame. So here we can see, let us consider by part very carefully. These are the numbers of joint rotation that may occur. So how many numbers of joint rotations are there? There are 5 joint rotation at the top level, and the first floor level there are 3. So there are 8 possible joint rotations. Let us consider this one, numbers of possible joint rotation. Let us sum it up. 8 rotations in the joints, rigid joints. In the hybrid joint there are 3 rotations. Mind it, here in the hybrid joints, the possible joint displacement will be numbers of joint associated with the hybrid joint minus 1, because we have to measure the rotation in terms of one rotation. So there are 3 rotations at the hybrid joints. Now let us consider the shear release. There is one shear release at here, so this will cause a vertical movement. Now there are 2 support rotations, one in this hinge and this roller. There are 2 translational movement, one in the roller joint, another in the guided roller. So support translations are 2. And there are 2 possible sways at the top of the frame and the bottom of the frame and the first load level of the frame. Let us now consider the cantilever frame, which is a part of this problem. So we may say there are 3 sways. There is a movement here, rotational movement, and a sway movement here. So 3 sways, and this will boil down to total as 21. So the kinematic indeterminacy will be equals to 21 in this case. So with this, I think we have discussed, and it is possible for the viewers to calculate the kinematic indeterminacy by their own without mugging up with some formulas and all this thing, with the basic concepts, and we can easily calculate the kinematic indeterminacy, whatever may be the complexity be there. Let us come to some conclusion on overall discussion of this lecture. Number 1, possible degrees of freedom will cause the joint with the kinematic indeterminacy, obviously excluding the restraints in the supports, and axial degrees of freedom is generally neglected except in the truss. Instability cannot be pointed out by degree of indeterminacy as it was in case of statical indeterminacy. But we have said that if the static indeterminacy is negative, we may say that the truss is instable, and it can be seen from the configuration also. Here we have to see it only according to the kinematic configuration, not by any number. So herewith we have completed today's lecture. Please feel free to put any suggestion, and you may put any question to the comment box that you are wanting to solve by me. And please give a like if you have liked this lecture, and don't forget to subscribe and share with your friends and colleagues. Hope that we will meet soon again with some other lectures in my channel. Till then, thanks a lot.